Hey, how's it going? Just heads up, we're actually going to be whiteboarding, so make sure you can see the whiteboard from where you're sitting. Someone in the back can make sure that, we'll get them back on when we start whiteboarding. Oh, that's perfect. Can everyone read that? Is that visible, legible, big enough? All right, cool. Let's do this. So, my name's Dan. I'm from Mozilla. You might know us for Firefox and/or Firefox Developer Edition. If you've been using Chrome because you're a jerk and you hate free software, check out firefox.com/developer. We've been putting a whole lot of effort into trying to make sure that Firefox's tools, Firefox's performance are best in class. And Dev Edition is kind of where you start seeing the new features before, like 8 weeks before they hit the beta and stable releases. So that's my pitch. If you have complaints about Firefox, also talk to me. But we're not here to talk about that. We're here to talk about the lie that we tell ourselves in the scripting language communities, that Python's fast enough or Ruby's fast enough. And when it's not, I can always write a C extension. Has anyone ever used that to justify using Python or Ruby to a boss? Yes, one person? Yeah, did it work? Oh. So out of curiosity, who here uses one of those languages, like the Ruby, Python, Node.js? Okay, everyone. So you're kind of familiar with that justification to yourself of I know that those languages might be faster, but this is probably going to be fine, right? It's this isn't an unfamiliar thing. But the reason it's a lie is kind of twofold. One is that the languages sometimes aren't fast enough for certain workloads, and we never actually do write C extensions. Has anyone in this room ever actually written a C extension to a scripting language? Why? Because somebody else already did it for you, and you just had to build the glue, right? Oh. Right. But so sorry. That was yeah. There's another point that I want to reinforce with that. But the idea is that there's this huge base of code in C that sometimes you have to use, right? And the way you do that is by writing more C. But if you were trying to build that library from scratch, right? Would you have chosen C? Right, because C is scary. Oh, whoops. So why don't we write C? The number one reason is that other people did it for us. So if you look at in Python, there are projects like this. The Python interpreter itself, 400,000 lines of code in C, which is 43% of the code base. Almost half of Python is written in C. NumPy, which is a numeric kind of computation library in Python, over half of it is written in C. Pillow, which is an image processing library, 40,000 lines, about half and half between C and Python. There's a Python micro framework called Flask that's super nice, super minimal. It relies on a templating library called Jinja2, which relies on an HTML escaping library called MarkupSafe, which is 800 lines of code, 200 of which are C, in a file called speedups.c. So people are writing a bunch of C, and we're able to avoid writing C ourselves because we can stand on their shoulders, right? There are all these existing libraries that are absolutely fantastic. They're written in C, and most languages, like the gentleman in the back said, have good C binding support. So if you find something like libjpeg, Pillow, Firefox, Chrome, all link to the same 90,000 lines of C JPEG library. And that's 90,000 lines of code that didn't have to get reinvented each time someone needed to render a JPEG in a different programming language. So C is fantastic because it is kind of the Latin of computer science, in that if you can write it in C, you can probably bind it from any other language. But C is super scary. Writing C is terrifying. And it's terrifying because memory management's hard. C doesn't have any safety belts. So C is fine if you get out of the car, go down the slide, get back in the car. C is okay with you doing this. Right. You accomplished two things at once very efficiently, but it was kind of dangerous, maybe?
It's also running kind of slow.
So yeah, C will let you do anything, but that means that you have to do a lot of things manually. You have to make sure that you allocate and free memory yourself. And when I talk about allocating free, when I talk about memory management, when we look into the difficulties there, you see bugs like Heartbleed, Ghost, the bug that didn't get the memo that vulnerabilities were supposed to have cool names, CVE 2015-80, which is actually a bug in the Internet Explorer PNG decoding, that if you fed IE an invalid PNG that was incomplete, instead of just rendering all the information in the file or like rendering a broken image, it would try to fill in the missing bits by just pulling other memory from the process space at random. So if you load enough of these and you use like Canvas and Postmessage, like you could exfiltrate the entire process space of Internet Explorer. And so, and I'm not saying that because I work for Mozilla and I'm trying to pick on Microsoft. They're doing really cool stuff with Spartan that just got renamed Edge. Like Microsoft's trying to get on board the standards wagon. I mention that because it's hilarious, and I look at it and I say, wow, I am not smarter than the glibc or the OpenSSL developers. Like if I tried to write C, I would make things worse for the world. And that's kind of terrible because sometimes you have to write C, right? Sometimes you have to write the next NumPy or the next matplotlib or the next who knows. And so if I was in the position of needing something that had C's portability, C's performance, and C's embeddability, I would really want to be able to get that, but with guaranteed safety, right? I would want the language to prevent me from like making a Heartbleed style vulnerability or making a PNG decoding security bug. And so that's what Mozilla is trying to build with Rust. We have a research project called Rust that's been under development for about 6-7 years. It started as kind of one guy's side project, and about a year later, people were like, "Oh, that's kind of interesting. Maybe this is worthwhile." And do you know how many people are in the Rust team? No.
About, I think 20 or 30 in research at the moment.
Yeah. So we've got like more than a dozen full-time engineers.
Outside of Rust contributors.
Yeah. I think the latest release of Rust had something like 250 people that had commits in a 6-week cycle. So this started in Mozilla, but it's very much bigger than Mozilla, trying to make this language that actually competes with C and C++. So anyways, we're talking about systems level languages, and systems level languages tend to be differentiated from other programming languages in that you have to actually understand how memory works, how the computer deals with memory. And predominantly that means you have to understand the difference between memory on the stack and the heap. Refresher, stack, super fast, managed by the CPU to hold your function locals. You enter a function, the arguments get passed on or pushed onto the stack, you exit the function, they automatically get popped off. The problem with the stack is that if you need to store something of variable size, like an array, or a vector rather, then if you append onto it, it grows in size in memory. And because the stack is compact, that might clobber other data on your stack. So we have a different area of memory called the heap that we use for these things that need to be dynamically allocated, that need to be resized. So the heap is where you store globals. It's slower, but it's effectively limitless. It's limited by like your bitedness of your CPU and your physical RAM. But it's unmanaged. And that means that you have to make sure, or your programming language's runtime has to make sure that whenever you put something on the heap, at some point in the future, it gets removed from the heap. It gets freed. That memory gets returned to the system. So let's talk a little bit more about this using actual code. So I was going to, on my flight down, I made a bunch of note cards and a bunch of illustrations. So I wasn't sure I'd be able to whiteboard, but there is a whiteboard. So if everyone can see or move so that you can see, I think we'll do this with actual whiteboards. What I've got, so what I've got here is a very simple Rust program. And ignore the fact that I have this inner block. We'll be adding things outside and around this block later, so that's kind of there for future illustrations. So this is pretty simple. We hit this line, we say let x equal a vector that has a, b, and c in it. So when we hit this line, when execution starts or gets here, we have to store the vector itself, the x, on this stack, but then this variable size data, a, b, and c, goes on the heap. So go ahead and say a, b, c. What do we need on the stack for the vector? What needs to be x up here? Anyone? All right, so we need a pointer. So we'll call it PTR. So we got a pointer to the head of this region of the heap. Do we need other things?
It depends how space you want to be.
Rust wants to be really safe. We need length. So all right, so the length right now is 3. And we actually need one more thing. Anyone know?
Reference count, maybe?
No, Rust doesn't use reference counting, which will be super interesting in a second.
How much memory you allocated may not be 3.
Yes.
Track that too.
So we want to track the capacity. So in this case, let's presume that we allocated perfectly because we're using a macro and it did it right. So if we were to try to push another element onto this, we'd have to go and allocate more memory. We'd have to allocate memory with at least capacity 4, copy all this over, add the thing on, then update the pointer, right? That's memory. So X is kind of represented by 3 kind of word-sized chunks on the stack: a pointer, a length, and a capacity. Oops. So we get here, we're trying to print line X subscript O. So we go to X, we follow the pointer, we don't offset any. Standard out says A. Hooray, we win. What happens when execution gets here? And where's my eraser? So we've exited this inner block.
Well, in a C program, you just lose your X on the stack, but the heap would remain.
Exactly. So X gets popped out. And we still have these 3 32-bit characters. They're Unicode. Rust characters are Unicode, so 4 bytes each. We've leaked 12 bytes. What would happen if we were using Python or JavaScript or Ruby? Right, so at some point in the future, your program is going to stop running so that you can walk the stack and see, all right, what does everything point to, and clear out the things that don't have any way to access them. Super convenient because it means that you can't forget to clear out memory, but super inconvenient because it means that at some point your program is going to like stutter and stop while the GC runs. Rust actually does something kind of in between the two. Rust manages memory automatically, but without using garbage collection. So what Rust does is the compiler itself introduces a notion of ownership. So when we hit this first line, we declare X, got the pointer 3, ABC. The compiler will statically analyze this code and say, OK, I'm going to allocate memory, and I'm going to give that memory to X. So the compiler will keep track of this separate notion of owner. And it'll say, all right, these 3 32-bit regions are owned by X. And the lifetime of this memory on the heap is going to be statically analyzed and bound to the lifetime of the variable X. So we'll hit this line, we'll print A, and then when we hit this line, X goes out of scope. And the compiler knows this. Just like we can read this without running the code and know that like at this point, this lexically scoped X is no longer accessible, so can the Rust compiler. And the Rust compiler can basically insert a little free right here, right before we exit that scope, which will go and clean up that information. Kind of cool, right? This is basically doing C-style memory management, so you can get roughly guaranteed performance, like soft real time. You know that you're not going to have a GC pause, but without you having to actually manually track, all right, am I done with this yet? Can I free it yet? The Rust compiler does it for you. Any questions on that so far? Yes?
What does that do to your compile time?
You pay a little more up front on the compile time, but it's really not bad. Like, we don't have like a Turing-complete template language like C++. So we're not as fast as Go, but we tend to be faster than C++. All right, so let's try to trick this. Yeah?
If things fall out of scope, doesn't that mean that you're calling free all the time?
Basically.
And doesn't that give you overhead?
It gives you overhead, but it's equivalent to like if you were doing this manually, unless you want that memory to stay resident until the program exits. And you can actually annotate this and say statically allocate this, so never free it until the program ends.
It seems like that's one of the advantages of having a garbage collector. It sort of does all those things at once.
Right. Yeah, you pay the cost of like, instead of all these little very, very tiny calls to free, you have it kind of stop the world,
And there's overhead on the garbage collector because it also needs to figure out which things it can free, and that's not
Yep.
trivial.
That's true too.
Ultimately, this is what you
Exactly. But you can't make a mistake.
Because you're, yeah, other than forgetting to do it.
Right. Yep. So let's try to trick it. Let's say we wanted in this block to actually set up something that lived longer than the block. So let's say let y. So Rust is strongly and statically typed. So all of these things that we're doing have compile time known types. But we never have to annotate them because, well, we rarely have to annotate them because the compiler is, wow, my handwriting just went horrible. The compiler is pretty smart about inference. All right, so we're going to declare a variable y, going to set up our x vector. After we set up the vector, let's say y equals ampersand x. So we're going to give y a reference to x. Print things, then try to use y down here. So same thing happens. We get here, so we know that y is going to be a reference to x, so we'll set aside just one space for a pointer up here. We'll have x here with the pointer len cap 3, 3. We hit this line. We provide y a pointer down the stack to x. Print out a, which works. This is owned by x. X goes out of scope, so all this stuff goes away. What happens here? We've got a dangling pointer. So this is a huge security risk. But it's cool because the Rust compiler, just like we could walk through this, we'll look at it and be like, nope, memory unsafe, not going to let you do that. You'll get a compile time error. And to prove it, we'll come over here to them. So I got the same code. If I try to compile this, oh, whoops, hang on. Need to subscript these. I got a different error for a different reason. We want the error that I'm talking about. So error, x doesn't live long enough. Reference must be valid for the block suffix following statement, blah. Note, barred value is only valid for the block suffix following statement 0. So the compiler itself is telling us, hey, wait a second. You're referencing this thing, but it doesn't live long enough. It goes out of scope. Like the y lifetime spans the entire function, but the x lifetime only spans this inner block. And so if this is referencing x, y can't live longer because the x reference is going to be invalid. And this is checked for us at compile time, which is super rad. So if we want to fix this, let's try.
What if we assign something else to y after, before x went out of scope?
Let's find out. Let's say, yeah. All right, so I'm gonna cheat and reveal something in the future. Everything is immutable by default, so we have to now say that y is going to be reassigned. Mismatched types. Yeah. There we go. So this is going to fail because Rust run. Bar value is only valid. Bar value does not live long enough, so we need to static.
That's frustrating. It doesn't let you write bad code.
Right. I forget the actual syntax for manually annotating static lifetimes on stuff. Whatever. I'm going to stop flailing. And I just know that Rust will not let you do things that are memory unsafe. But let's say we actually did want y to outlive this block, and we want it to be initialized inside the block. If instead of giving y a reference to x, we just give y x, then what we do is we'll set aside space on the stack for an entire vector. Then we'll go initialize another one, x, which will point down there, a, b, c, 3, 3. When y equals x, we'll actually copy this entire struct on the stack from x into y. So we'll get another pointer that will actually alias down there. Capacity 3, length 3. Does that make sense? So like raw assignment copies the actual value on the stack. But Rust also has that notion of ownership. So when we got here, we knew that this area of the heap was owned by X. But when we reassigned X to Y, that's equivalent to passing ownership to Y. So the compiler will note this and be like, all right, at this point, this area of the heap should be freed when Y goes out of scope instead of when X goes out of scope. Then we try to print X sub O, which should work because all the data is still there. But we can't guarantee it. One of the limits of the ownership system is that if you give something away, you don't have the right to access it anymore. So even if that data is still there, even if it would still work, Rust won't let you actually print this line. So proof. Error, use of moved value. That value is no longer in X. It was given to Y. So even if the data is still in memory, we can't guarantee that it's safe, so the Rust compiler won't let you do that. So if we comment out that use of X, so the general rule is after you give something away, just like a physical object, you can't use it anymore. You can lend things out and still, like with that reference, but there's a different semantic for transferring ownership. So if we comment this out and try to run that, oh, whoops, Rust run. We see we get A on standard out, so it works. Does everyone follow? Questions? Yes.
So when you do the owner transfer, does it automatically go like top to bottom? So if Y were lexically scoped with X and it were assigned later, or does it go by like whatever variable has the widest scope?
It does go top to bottom.
Okay.
So you have to make sure that the compiler will yell at you if you get the order wrong, and it'll give you a helpful description. Programming Rust, something you will never see if you just read Rust code that works or just run things written in Rust, you will never see the borrow checker in the compiler yelling at you. If you ever try to write Rust, most of your life will involve the borrow checker yelling at you. It takes a couple weeks, and then it makes sense, and then it's amazing. Everyone follow that so far? We're good? Any other questions? All right. So the general rules for ownership is that you can only have one unique owner per allocation. That's why when we moved this, the owner table got updated and X was invalid. So, I went in wrong order. Ownership can be passed, but it invalidates the prior owner. The second bullet is that memory is freed when the owner leaves the scope, and the implication of that is that every other thing referencing that same region of memory has to be out of scope before the owner leaves the scope. And then refs are created with the ampersand. We call them borrowing in Rust. And all of this is enforced at compile time without adding any runtime overhead to your code at all. You pay up front for the compiler to double check your work. And then once your code compiles, you are guaranteed that there are no dangling pointers. There are no use after free vulnerabilities. There's no pointer arithmetic in Rust. There's no fear of having a null pointer dereference because the compiler has your back. Zero cost at runtime. Super cool. So it's like lets you write C performance, C degree, or code that performs to the degree of C, but without the unsafety of C. And we actually, the borrow checker is written as part of our compiler toolchain, but we actually feed Rust into LLVM and compile there. So optimizations that happen in LLVM also benefit Rust. So we're using a mature toolchain and trying to add more semantics and more safety on top of it. Let's talk about mutability. So we're going to do this with demos too. So in Rust, everything is immutable by default. So in this code sample, which we can probably make even a little bigger, I've declared x to 1, I try to increment it, and then I try to print it. If I run this, error, reassignment of immutable variable x, note prior assignment occurs here. So if I want to be able to change a value, I have to declare it as mutable. If I do that, I get 2. Explicitly containing and declaring what is mutable and what is not mutable is absolutely crucial to some of the compile time safety guarantees that Rust can make. This lets us reason about how is your code actually going to be used. Rust at compile time, if you're writing multi-threaded code, prevents all data races, period, because of that sort of system. let's do something a little different. So I've got a function main that defines a mutable variable x with the initial value of 5. We pass a mutable reference to x into this add1 function. Add1 function takes a variable called num. It's a mutable reference to a 32-bit int. It dereferences num, increments it by 1. Actually, yeah, we can do that. And then we come down here and print it out. So if this works, we should come up here, dereference to get a reference to the actual 5, increment it, we should print 6. Does that make sense to everyone? Side note, when I'm doing this rust run command in Vim, all that's doing is invoking rustc and then my file name. So the Rust compiler is running and it's just spitting out the output. So I run this, I see 6, it worked. Let's try to refactor this. Let's say that we don't like this parameter here. That looks ugly. So let's pull it out. So the only thing, let's close that, close that, close that. So the only difference between these two code bases is that in this file, we've taken that and mutex, given it another variable named y, and we passed y into add1. Will this compile?
Probably not. Otherwise, you wouldn't be showing us.
Right. And the last one compiled. So the interesting thing here is that if I try to run this, or try to compile this, error, cannot borrow x as a mutable because it is also borrowed as mutable. So one of the rules that Rust enforces is that there can only ever be a single, unique, mutable reference to memory. So as long as y exists, as long as there is a path that lets you mutate that data, nothing else can read from or write to that data. You can't have any other pointers outstanding that let you mutate that same region of data or let you read from that same region of data. So how do we get rid of this? The problem is that y is in scope. And as long as y is in scope, we can't read x.
So could you just put a block around those two lines?
Yep. Bingo. So this is actually super important because when you look at languages like Go or Python, and you look at how they handle data races, how they handle parallelism and multi-threading, Python and Ruby both have global interpreter locks in the C implementations, which means that even if you try to spin up a bunch of threads, only one of the threads can actually make progress at a time to prevent data races. So it's like, all right, it's kind of scary if two things can read from data at the same time and one might be writing to it. Like you might get an incomplete read, you might read stale data, you might clobber each other. So Python and Ruby say like, all right, even if you have multiple threads, we're only going to let one of them actually proceed at a time. So it gives you as a programmer, it gives you some benefit, but not in terms of like reasoning about your code and structuring your code, but not in terms of performance. Look at things like Go. Go tries to avoid, idiomatic Go doesn't actually prevent this, but what Go does is it has the mantra of share memory by communicating instead of communicating by sharing memory. And so what Go wants you to do is to send references across a channel, and then after you send that reference, to like promise that you'll never read it again or use it again. And so kind of pass it like a baton around. Not enforced, but it's a different philosophy. Rust says, no, memory is a great place. It's fast. If you have multiple threads, they all share the same memory regions. Like it'd be super useful if you could actually reuse immutable structures, or if you could actually constrain mutability and make sure that you're doing it right. Because that's what we're trying to get to. We're trying to make sure that our multi-threaded code isn't going to do something dangerous. And Rust does this by checking that your code is safe at compile time. And this isn't just, oh yeah, question?
Sorry, I guess I didn't follow this completely.
Yeah.
So how come it's not complaining about mutability when we're saying let y equal the pointer for x?
So it's not complaining because once we exit this block, y goes out of scope. And so down here, y doesn't exist anymore.
Right.
And so once y doesn't exist, it's like having a mutex or lock on memory. And as long as there's a mutable reference that's been created, nothing else can read or write until it goes out of scope to release that lock. Does that make sense?
Can read or write.
Right.
Okay, but isn't add1 writing to it?
It is. So we're actually, so the mutable, yeah, okay, good question, cool. So we're passing in this mutable reference.
Mm-hmm.
What's happening there is that, all right, let me try to speak carefully. If you have a mutable reference to something, you can give that away to other things. You can pass it down the line. You just can't duplicate it or fan it out. So basically, y is being given to add1, and then add1 uses it. Then add1 gets done with it.
I get it. So we're saying it's because it's and mutable x and not
Yeah.
just and x.
Yep.
Okay, got it. Thank you.
When y is assigned to a mutable reference to x, does that do anything with the owner? Is x still the owner?
X is still the owner. So anything that has an ampersand or an ampersand mute is just a pointer, just a reference. So it doesn't actually copy the structure. It doesn't actually change ownership. Cool. This, if you can grok everything I've told you, like if you think you are kind of getting what this is doing, you're in a really good place. This is the stuff that takes weeks. At least took me like 3 or 4 weeks of trying to read the docs, trying to test things, trying to read the docs. So also don't feel bad if this is kind of like, but this is the crux. Like you have to kind of understand this stuff before you can write anything non-trivial in Rust, and sometimes even before you can write trivial things. There's a great blog post about fizzbuzz in Rust. Yeah, why your first fizzbuzz implementation may not work. So Rust has these concepts of lifetimes, ownership, borrowing, and you have to kind of understand all 3 of them at once before you can write anything. And so Chris Morgan wrote this, short article on how to implement fizzbuzz in Rust and how to then optimize it. But talking about all the different things about static typing might prevent your first go at this from working, how safety concerns might prevent your first go working. It's a good read. It's also a really intimidating read. I like this a lot better. So all of this isn't just for the sake of being pedantic, for the sake of being academically correct. The Rust programming language has been co-evolved and co-developed with an experimental project called Servo inside Mozilla. And Servo is a next-generation browser rendering engine. Right now, basically every engine, every major browser engine is single-threaded. You may have multiple processes per tab, but fundamentally, layout, painting, all that is done in a single thread. And that's super sad when our CPUs aren't getting faster themselves, but we are getting more of them. And so we started to wonder, what would it look like if we, one, had a language that prevented all the security vulnerabilities that you've heard about, like that PNG decoding bug I talked about earlier, that prevented that at compile time, but that also had facilities to make sure that we could actually write concurrently executing parallel code deeply into the browser. And so Servo is pathologically parallel, and it works. Like Servo's been under works for like 4 years-ish. That's it rendering GitHub. So we built a browser engine from the ground up that can actually render websites. We render about half the web. So it does GitHub. It also will do Reddit. And you may look at that and be like, ooh, Dan, this is not going to go so well. That's actually a debug screenshot of Servo. Each different color box indicates what CPU did layout on that element of the page. Academic things had to happen to make that possible. Like state-of-the-art research on can you do layout parallel. And it's only been the last couple of years that we think we've cracked how to do a lot of it in parallel. And the cool thing is, if you actually do this kind of pathologically parallel design in your browser, you get amazing performance. So right now, Servo will go about 40% faster than Firefox will, which is interesting because if you underclock your CPU as low as the voltage will go, you usually lose maybe 30% of your performance. So if you're looking at instances where like, I've got a phone that has 4 cores on it, but I care more about battery life than performance, well, with Servo, I can have both. We can underclock the phone, get better battery life, but use a more efficient engine that actually uses all of those cores at the same time, and still go faster than Firefox will or than Chrome will running at full bore. So this is actually like, you can download and run Servo today, and it will render most websites pretty well. We've got it rendering things like you saw at GitHub, we've got it rendering the Steam Workshop, or the Steam Game Store. We're right now actually looking to ship this, not as a replacement for Firefox, but as a replacement for an embedded WebKit or an embedded Blink. Servo actually has I believe, an identical API, if not a very similar API, to the Chrome embedding format. So if you've already built a native app that embeds Blink or WebKit, you should be able to drop in and replace Servo. So one thing real quick that I want to show, we've got about 10 minutes left, are FFI demos. So one of the things that Rust is really good at, I've talked about how it's, let's see, we'll go into double. Talked about how it's C level, how it uses LLVM. One of the really important things for us in Rust is that we have absolutely trivial interop with existing C and C++ code bases. One of our goals for the end of this year, you can search on Bugzilla for the oxidation tag. We're trying to get something in Firefox to be built in Rust. We're targeting either image decoding or URL parsing as the first thing, but by the end of this year, if you download and run Firefox Developer Edition, you will most likely actually be running a hybrid C++ Rust code base. And our hope is that over time, we'll be able to replace more and more of Firefox with components written in Rust and have both a faster and a safer browser. So let's talk about how that interop works. So cd ext FFI examples. Let's go into double. So I've got a cargo file. Cargo is the Rust package manager. It's been developed by Yehuda Katz of bundler fame from the Ruby world. I declare a package named double, version, author. I'm going to compile this as a dynamic library called double. My Rust source is simply a public external function double that takes a 32-bit int, returns a 32-bit int, and it returns x times 2. Rust is an expression-oriented language, so the last expression in your function is what gets returned. And I've got a unit test down here. Because of this annotation, this will only actually be compiled if you're compiling with the test flag. So you're not going to bloat your binary size with code that's not actually live. And this asserts that double 3 equals 6. So I can come over here and say cargo test. Running one test. It works. OK. So we're good. We've got a Rust function that will double. To make this available to see, again, I have to declare it as external. And I have to make sure that this function name is not mangled, so that in the resulting .so file or .dll file, there is a symbol called double that I can get at, instead of something called like some random hash. So I can go into a Python program, double.py, and here I can say from CFFI import FFI. CFFI is a library that does libFFI style bindings from Python into C. I provide a C-style header. So I've got this function double that returns an int and takes an int. We want to be able to generate this for Rust in the future. Right now, you have to write the C header by hand. There's a program bindgen that will go the other way automatically. That'll take C++ code and generate Rust bindings for you, or Rust definitions, because you don't actually need binding. Rust doesn't have a runtime. And so down here, I say, all right, open this DLL that I just compiled called libdouble blah, 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 .dylib, and then call c.double3. So if I run this Python program, I get 6 out. So that's all it takes to call from Python into Rust and return back to Python. Absolutely trivial. And you can do this with any language that has C-style bindings. If it can bind to C, it can bind to Rust. But integers aren't super interesting because they're small, they can be passed on the stack. Let's try to do something a little more curious. Let's go into calc. Oops, where's my cursor? So calc is a function that takes a reference to a string, returns an integer. Inside here, we're going to declare a mutable accumulator started at 0. We're going to iterate over every character in that string. And we're going to match on that character. If it's a plus, we increment by 1, minus decrement, star, doubles, slash halves. And then we have this underscore for any other case. Rust match statements are exhaustive. If we left this off, it wouldn't compile because Rust knows that strings can have more than the 4 characters plus minus slash star. If you have an enumeration, like you have an enum that has 3 options and you have a match statement that only covers 2 of them, Rust will complain. So at compile time, Rust makes sure that you are actually exhaustively taking care of what this type could possibly return. And then we return that final accumulator value. There is a return keyword or function or expression statement, whatever language, if you need to early return out of something. But again, idiomatic Rust, the last thing that's in your function body is what gets returned. So down in our test, we say, all right, plus plus star minus slash. So 1, 2, 4, 3, 1.5. But we're using integers, so it'll be truncating division. So we should get 1 back. So let's cargo test. All right, our test passed. Let's do this from Python. So I need to have this really ugly thing, don't look at it too hard, that takes a constant C character pointer, converts it into a C string, then converts that into a string slice, and then passes that. Whatever, if you need to pass strings, there's documentation, it makes sense. But we'll not dive into that. The Python code I have, again, does the same thing. We return an int from the function calculate, which takes a constant character pointer called script. We open the DLL. We pass calculate. Let's see, so 1, 2, 4, 5, 10, 9, 4.5, so we should return 4. We print that result. 4. So again, C strings going from Python to Rust, getting it back. There is one last thing that I have time to do a demo of, which will be fun, and that's burn.py. Let's start activity monitor. Let's look at this library. Actually, look at this first. So Python, I was saying, has a global interpreter lock. How do I? There it is. Which means that only one thread can execute at a time. So I've got a function here that when we start a thread, we're going to use this function run. It's going to report that that thread started. It's going to start at 0. It's going to count to, what, 10 million? By incrementing one number at a time. Return. And then we get this function triple that starts 10 of those threads that count to 10 million. And when all those threads finish, it returns x times 3. So this helps us triple a number really quick because it gets our CPU really hot and like helps the electrons flow faster. But if I run this in Python, see my thread start, you'll notice that none of my CPUs get pegged because Python has the GIL. It has the global interpreter lock. So only one of the threads is moving at a time, and there's actually a lot of overhead, so we're not very efficient. That took, how long did that take? Maybe 14 seconds or so? Oh, here they come. About 8 seconds. All right, so let's do this in Rust. The Rust looks like this. Again, it's kind of crazy, but let's make it.
Reminiscent of Ruby.
Yeah, Rust has taken a lot of inspiration from Ruby in terms of like, here's a closure that takes a single variable I. We spawn a bunch of threads. We wait for them to return. We return x times 3. Don't worry about the syntax. This is all doing the same thing as the Python I just showed you. But if I run this, oh, hang on, that went way too fast. Oh, it does the same work in 0.45 seconds. And that's again, not because Rust is so much faster, but because it doesn't have the overhead of the GIL, and it is able to run all 4 cores at the same time. So let's make this go. Let's make this go calculate to 1 billion. You can arbitrarily add underscores in number literals to kind of make it more legible, which is kind of fantastic. So, right, yeah, like who would have thought? So if I run this, you'll see that because these are all running in parallel, this report looks all jumbled, which is good. And you see that my CPUs are actually being pegged. And so we counted way higher in 11 seconds, but like 43 CPU seconds, right? Because we were actually burning all 4 CPUs at 100%. And so we can do that from Python using the same thing. There's our function. We're going to open that. We're going to call 333. So if I run burn.py, we're sidestepping the GIL by calling from Python into Rust. Rust is then spawning threads which run in parallel that aren't part of the GIL. So while that Python thread is holding the global interpreter lock, Rust is going and spinning on all 4 cores. And then, oh yeah, sorry, I didn't time it. It should be basically the same. Which actually lets me do multi-thread computations on like a per function basis. So I can really easily say, this isn't fast enough, I'll go optimize it in Rust. And I actually get parallelism, like for real. And this ran actually faster than the previous example because, you know, the actual load on the system or whatever. But there's not significant overhead of that call. And that's kind of what I have today is this presentation of Rust. 1.0 stable comes out next week. So if you've heard about Rust and have been interested in it, now is a great time to start looking at it. The subreddit for Rust is actually friendly, which is kind of shocking. But yeah, I highly recommend check it out. It's a fun language. Please rate this on joined in 14086. And if you have any questions, you can email me, tweet me. I'm also, we've got like 15 minutes till the next speaker, so I can shut down the laptop and just talk for a while. But thank you guys so much.
Is there any kind of hook in for Arduino?
For what?
Like Arduino? Like that's like I hate